Minimum cost tree from leaf values. Let's check the question. Given an array of positive integers, consider all binary trees such that each node has either 0 or 2 children. So it can be a single node like this, or it can be a binary tree having 2 children, right? Or it can be a binary tree like this, where some nodes have 0 children, like this, or some nodes have 2 children, like this one and this one. Or it can be a full tree like this. Second thing that is mentioned in the question is the value of array correspond to the values of each leaf in an in-order traversal of the tree. Let's understand this with an example. So this tree has an in-order traversal which looks something like this. What is an in-order traversal? Basically, in an in-order traversal, we start from the root node and then we check whether it has a left value, right? It does. So we'll check whether this node has a left value. It does. And then we'll check whether this node has left value, but it doesn't, right? So we'll visit this node and then check whether it has a right value, but this node doesn't. So we'll visit the parent node. And once we visit the parent node, we'll check whether it has a right value. So before visiting this right value, we'll again check whether it has a left value. It doesn't, right? So we'll visit this node and check it's right. It doesn't. So we'll go back to the parent, and this is already visited. So we'll go back to the root node and then visit this node and then check for the right. And then before visiting this, we'll visit its left and so on, right? So this is how we get it, the in-order traversal. So what does this imply? Whatever leaf nodes which will be given to us in the form of array will be in an in-order traversal of the binary tree, right? So in this case, the leaf nodes come in the following order in the in-order traversal: 1, 3, 5, and 7, and that's what we will get. So if we try to construct the binary tree using this leaf nodes, then it should maintain this in-order traversal, right? Next, the value of each non-leaf node is equal to the product of the largest leaf value in its left and right subtree respectively. Now what does this mean? Let's consider the previous array that we just saw. So in this case, if we were to construct the binary trees, so how we will construct the binary tree? Let's consider 1. And here, what does it say? The value of each non-leaf node is equal to the product of the largest leaf value in its left and right subtree. But this is the leaf node, right? So it already has a value, right? But what will be the maximum value in this case? It will be nothing. It will be itself, right? So max value of its left and right subtree, it doesn't have any left and right subtree, right? So its value will be 1 itself. Let's combine it with 3, and similarly its max value will be 3 itself. How combine this and form the non-leaf node now? Non-leaf node will be the product of the largest leaf value in its left subtree and right subtree, right? So the product of these two is 3 itself. So what will be the maximum value of the leaf node in this node? Okay, what will be the largest leaf value of this node? Well, it will be the largest leaf value between the left subtree and the right subtree. So the largest leaf value between these two is 3, right? So we'll have the max value as 3 itself. Let's continue constructing. We'll now pair 5 with 7, okay? And once we combine this, the non-leaf value will be again the product of the largest leaf value of its left and the right subtree, right? So the largest value product will be 5 into 7, 35, right? And what will be the max value of this entire node, okay? This entire subtree, it will be 7. Now, what will be the value of the root node? It will be the product of, again, the largest leaf value of its entire left subtree, the largest leaf value of its entire right subtree, right? So what will it be? It will be product of these two. So it is 3 into 7, which is 21, right? This is one of the permutation possible, right? So this is what this statement means, okay? Now, among all possible binary trees considered, return the smallest possible sum of the values of each non-leaf node. So as I said, this is one of the binary tree permutation that we can form using this array, right? And what we are told to find? We are told to find the sum of these non-leaf nodes, okay? And that too the smallest possible sum of values of each non-leaf node. So how do we go about this? Well, what comes into mind is why not consider all the permutation of the binary trees that we can form given the array, right? Okay, fair enough. We can check few more permutations and then find out whether we can find any intuitive pattern in this question. So let's take the same example and construct another permutation of a binary tree, which has the following in order trapezoid. So of course, this is the first permutation that we have already seen, but the sum of the non-leaf node will be 59 in this case. 21, 3 plus 5, right? So 59, fair enough. Let's check whether we can get anything smaller than this, right? Let's start by combining with 5, 5 and 7. Okay, so 5 in this case will be max will be 5 itself. 7, it will be 7 itself. And combining this, the product of the left, largest leaf value in the left and largest leaf value in the right subtree is 5 into 7 is 35, right? Then what will be max? It will be 7 itself, right? Of this entire tree, subtree. Let's combine it with 3. The max value of 3 is 3 itself. Then combining 3 and 7, we get 21. So what will be the max of this entire subtree? It will be 7 again, right? Now let's combine 1 with 21. And here 1's max value will be 1 itself. And by combining, what will be the non-leaf node value? It will be 1 into 7, right? So it will be 7 again. So what will be the sum of this entire non-leaf nodes of this binary tree? It will be 7 plus 21 plus 35, which is 63. Okay, not better than the previous one, of course, right? The very structure of this tree suggests that we are going to get a greater value. But why? How did we start combining this tree? Well, basically, we started with the maximum values, right? The maximum values, the maximum pairs in this entire array is 5 and 7, right? And while combining, the maximum value that we pass to the next subtree, the next level on the subtree is 7. And at each level, we are passing the same maximum value. And of course, the maximum values will be, the product of the maximum values will be maximized, right? Because at each level, we are passing the maximum value, right? Let's consider another permutation. Here, let's start by combining 1, and its max value will be, of course, 1, with 3, its max value being 3. Combining them, we get 3. So what will be the max value of this entire subtree? It will be 3 itself. Then let's combine it with 5, which is the next max value in this array, right? What will the max value of this node? It's 5. Combining them, we get 15. And what will be the max value of this entire subtree? It will be 5. Let's combine it with 7 now, the final node value. And what's the max value of this one? It's 7. By combining this, 5 into 7 is 35. Now what will be the sum of this? It's 53. Why is it smaller? Why is it smaller than the previous one? Now, if you check the structure of this tree and at each level what max value we are passing, then you get some understanding to the problem now, how to solve this problem. Because at each level, because at each level we are passing the minimum max value, right? We have considered the minimum pair first, and then we are combining it with the minimum max value at each level. This is how we proceed, right? And that's why we are getting the minimum. And I can assure you that this is the smallest sum that we can find, no matter what permutation we consider of this binary tree, no matter what. And I can tell you that because of the structure of this tree, the way we are combining them, right? And you can check the in order traversal property is preserved. To understand this concept deeper, let's check another permutation. Here, let's combine 3 with 5. By combining them, we get 15, and the max value of this entire subtree will be 5. Let's combine it with 1, right? The max value of 1 is 1 itself, and combining them will get 5. And what will the max value of this entire subtree? It will be 5 again. Then combine it with the final leaf value, which is 7. And then what is the non-leaf node value by combining these two? We'll get 35, right? And again here we can check the sum will be 55, which is greater than the previous one. And the answer is simple. The structure, the way we are combining it, the structure of this tree and the way we are combining it, we are combining randomly, right? We haven't actually chosen the minimum max value, right? That's why. So finally we understand why this is the minimum sum. So to summarize, minimum sum is nothing but the sum of the product of minimum max values, right? So whatever max values that we are going to send at each level should be minimized, right? Because if those max values are minimized, then we can assure that the product will be minimized, right, of those max values. And if the product is minimized, and the value of each non-leaf node will be minimized and their sum will be minimized, right? Hence, this is how we solve the problem. We can traverse it from left to right direction, or we can traverse it from the right to left direction, whatever suits. But while traversing, we need to keep in mind that the way we combine them should maintain the in order traversal property that we saw in the first statement of the question. Okay, so in this case, let's traverse it from left to right and check the increasing order, okay, the minimum increasing order pairs, so that we can pass at each level the minimum max values. Okay, so in this case it will be 1 and 3 combined, so our non-leaf node value will be 3 and max value that will pass is 3. 3 will be next combined with the minimum value, that is 5. I mean minimum leaf value, that is 5. And by combining them we have 15, and the next minimum max value that we pass is 5. And that's how we do for the next as well. So if you can see, this is monotonically increasing. This max values, we are monotonically increasing. So that's what we are going to use, okay, to solve this problem. So here it's simple, okay. Of course, this is in ascending order, and hence we get the values directly by traversing from left to right, right? Minimum values. But what if we were given a array like this, which is in descending order? Okay, simple. The concept remains same. The minimum sum is again the sum of the product of minimum max values, right? So in this case, we'll again traverse from left to right and check whether we get a value which is in increasing order, right? So here, if we check, 7 is of course greater than 5, so we cannot combine it yet. 5 is greater than 3, cannot combine. 3 is greater than 1, cannot combine, right? We are absolutely sure that this is in decreasing order, right? So we'll now combine it from this direction. So 1 will be combined with 3, and similar way 3 will be combined with 5, and 5 will be combined with 7, and at each level we get the minimum non-leaf node values and then minimized max values, right? So let's consider another example. It's neither in ascending order nor in descending order, okay? So in this case, let me shift it down. So in this case, how are we going to go about traversing this? It's simple, okay? So the first thing, we are obviously going to start from left to right. So since first value is 14, but there is nothing before that, so we have nothing to compare it with, right? So we'll start with 11. 11 is less than 14, so this is decreasing, right? So of course we can find more decreasing values, right? There can be a value that can be lesser than 11, right? So we will have to combine them first, right? So I'll go to the next value, that is 3. So 3 is again less than 11, so of course this is in again decreasing, so there can be a lesser value than 3, right? So we'll combine them. So 3 next to 3 is 9, right? Now 9 is greater than 3, so that means this is an increasing order, okay? It's not possible to combine this 3 with this value or this value. The reason being, if we combine it with this, the max value will be 11, right? And if we combine it with 9, the max value that we'll get in that level is 9. So which is the minimum in this case? The 9 is minimum, right? So we need to minimize the max value, right? So the minimum max value by this combination will be 9, okay? And of course we cannot combine these 3 with this. Why? Because we have to maintain that in order traversal value, right? So that's why we combine these two, okay? So we combine 3 with 9, we get 27. And what will be the max value in this entire subtree? It will be 9, right? Now check whether we can combine this 9 with this 11. Well, we can, but it's less than 11, right? So there can be a lesser value than 9, and that combination we can find in the next by traversing this array, right? So we'll wait before combining them, okay? So we'll move on to 3. 3 is less than 9, right? So again we can find another combination which is lesser than this 3, right? So we move to 2. Now 2 is less than 3, right? So but there is nothing after this, we have reached the end of the array, so we directly combine these two, right? We combine 3, we combine 2, we get 6, because this is now the minimum pair in this entire array, right? This entire array, this is the minimum pair. So we are now sure that this is in decreasing order, right? 14, 11, 9, 3 and 2 is in decreasing order. That's why we combine these 3 and 2. We combine and we get 6, and the max value of this entire subarray will be 3. Now combine 27 and 6. Why? Because 9 and 3, okay? The next minimum pair that we can get is 9 and 3. So we have to minimize the max values, right? So it will be 9 and 3's product. So that is 27. So the max value of this entire subtree will be 9. 9 now will be combined with the next minimum max value, which is 11, and combine 11 and this 27 here, and we'll get 11 into 9 is 99, and the max value will be 11. And then finally we combine 99 with 14, because that's the last value remaining, and that's its max value will be 14, and 14 will be multiplied by 11, and the non-leaf node value will be 154. And finally the sum we will get is 313. Okay, so we understand the entire concept by traversing this, because at each traversal we are uh, we know that this is decreasing in order, right? And if we find anything in increasing order, then we combine them, right? But ultimately, once we are through this array, once we have traversed this array, we know that this is in monotonically decreasing order, right? So we combine we then traverse it in the opposite direction, because we are sure that we will always get the minimum pairs, okay, minimum max values at each level while combining. So how can we achieve monotonically decreasing order? By using a monotonic stack, right? So that's what we are going to do now. We are going to traverse this array using monotonically decreasing stack. So stack that we are going to use will be initialized by infinity. Why? There's nothing to compare this 14 value with, right? So that's why we compare it with infinity. So that's how we know that this is always in decreasing order, right? If once we initialize this stack with infinity, we start traversing this. So of course, 14 is less than infinity, right? So we insert it in the stack and we move on to 11. Now 11 is compared with the topmost element in the stack, which is 14. Now 14 is again greater than 11. So we insert 11 into the stack, we push 11 in stack and we move on. Now 3 again is less than the topmost element in the stack, which is 11. So we again push 3 in the stack and we move on. Then 9. Now 9 is greater than 3. So finally we found an increasing. Okay, so this actually disobeys the property of monotonically decreasing order, right? So we combine them. How do we combine them? We pop the element 3 and we combine it with 9 and the product is 27. So this will be the first non-leaf node value that we have, right? 27. Now this combinations 3 and 9, max value between these 3 and 9 is 9, of course, right? So 9 is our next max value. Now 9 will be compared with the topmost element in the stack, whether it is greater or lesser than this element. It is obviously lesser. 9 is lesser than 11. So it obeys the monotonically decreasing order property. So we will push 9 on top of the stack and move on to 3. Now 3 again is lesser than the topmost element in the stack, which is 9. So 3 will be pushed in the stack. And finally 2 being lesser than 3 will be pushed again in the stack. Now we have reached the end of the array, right? So we will pop this entire stack, because we are sure that this entire stack will yield us the minimum max values, the minimum pairs, okay? And each minimum pair will give us the minimum max value at each level, right? So 2 will be popped and 3 will be popped and combined and we get 6. Then the combination 2 and 3's max between them is 3. So 3 will be combined with 9 and we get 27 again, right? And 9 will be combined with 11 and we'll get 99. And then again 11, which is the max value, will be combined with 14 and we'll get 154. And finally we get the minimum sum as 313. I hope the concept is clear to you, and let's see the code. Let's start with the code. So let's initialize the result value as 0 and let's initialize a stack with float infinity, and then let's start traversing our array for each A in the array while stacks topmost value is less than the array's value a, we will, so what does this statement means? It means the monotonically decreasing order is disobeyed, right? So this is increasing in an increasing order, right? So in that case, we are going to find our result, right? So how do we find the result? We'll first pop the topmost value up, and then we are going to calculate the result by getting the product. So this result is actually plus, right? So by multiplying the topmost element with the minimum of the stack's topmost element, comma a. You understand this? So we want to minimize our max values, right? So we'll get the minimum out of these two, okay? And then we'll take the product and we'll add it to the result. And once we get the topmost value as greater than the value of a, right? Then we will simply append that value into our stack, right? Okay, so this way we have reached the end of our array, right? So now what do? We will now start popping our stack, right? So whatever is remaining in the stack needs to be popped out and combined as well. So while length of stack is greater than 2. Why greater than 2? Because we have already initialized this stack as with one value as infinity, right? So we need at least 3 values in the stack to combine, right? With those 2 values we can't combine, right? We need at least 3 values in the stack to combine the first 2 values and leave the infinity alone, right? So that's what we are checking here. And then we calculate the result equals to stack dot multiplied by stack's topmost element. So if we have 3, we know, right? If we have 3 elements, we are sure to get the correct value here, right? And then finally we return the result. I have written this spelling wrong. Return the result. Let's run it and check. Accepted. And yeah, I think this is clear. Thanks everyone, and I'll see you later. Bye.